Hello everyone. So in this video, I'm starting more discussion going into more depth of the classification section. In the last three videos where we did the complete end-to-end project in the machine learning, we have mostly used the regression. And as I mentioned that most common supervised tasks are regression, where we are predicting the values, and classification, we are predicting the classes. So in the previous three videos, we explored the regression task, predicting housing values using various algorithms such as linear regression, decision tree, and random forest. Now we are turn our attention to the classification systems. So in this video, I will be using the MNIST dataset, which is the set of 70,000 small images of digital handwritten by high school students and employees of the US Census Bureau. So each image is labeled with digit it represent, and this set has been studied so many that is often called the holy world of machine learning. Whenever people come up with a new classification algorithm, they are curious to see how it will perform on the MNIST dataset. So scikit-learn provide many helper function to download popular dataset, and MNIST is one of them. So the following code here it fetches the MNIST dataset from the openml.org. So here I'm just importing the libraries which we are going to use, and this is the dataset to fetch it. So I'm not executing the code because uh, to fit this model and it's take a lot of time. So I've already executed and this is the datasets. So open fetch ML means this part it's a function a bit unusual since by default it returns the input as a panda data frame and label as a panda series. So but MNIST dataset contains the images and data frame idle for that, so it's preferred for the as frame equals to false. So there are 70,000 images and each image has 784 features. This is because each image is 28 by 28 pixel and each feature simply represent one pixel. So 28 by 28 is 784. So that's why the shape of this particular data set is 70,784. And let's take a peek at the one digit. So if I, this is a function which takes the image data as the input and it's reshaped back to 78 by 78 means one digit it will show you, and that's what is right. So this looks like a 5 and indeed when we check with the y label, so y is the label, right, and it shows that this is the actually the 5. So our interpretation is correct here. So open fetch open AML is usually is actually already splitted our data into the training set, that is the 60,000, and the last 10,000 images as the test data. So this is what the first 60,000 images as the test and the seven remaining 10,000 as the test data set. So training set is already shuffled for us, which is good, and this guarantee that all the cross validation fault will be similar. So some learning algorithms are sensitive to the order of the training instance, and they perform poorly if they get many similar instances in a row. So shuffling the data set ensure that it won't happen. So we don't have to do the shuffling here. And so we have a lot of big data set here, right? And what we are going to, we will simplify our problem. So we'll start with training a binary classification which will choose only the digits which are 5. So if in all the images, if it is 5, then we are considering that is the what we want. If it is not 5, so it's become a binary. So we can call it like 5 detector. So 5 detector will be an example of the binary classifier capable of distinguish between just two classes 5 and non-5. And first we'll create the target vector for this classification task. So this is the Y train. So on the Y train which was label, we just equal to 5. So this is our target label. And this is that for the test. We again advertise. Then we are making it as a test label. Now let's pick up classify and train it. So a good place to start is with the stochastic gradient descent (SGD) classifier. So using the scikit-learn SDGD classifier, so we can import from there and use the random set for so you can also get the same results, fit the model of X train and the Y train. So once it fit the model, we can predict for some data. So some data is just nothing but the first value and it's performed the value is true. So look like the guessed right in this particular case. But before we move ahead, let's also discuss the performance measure, which is really important. So in the regression task, we have used the multiple, actually two, the mean square error and the absolute square error, right? So measuring the accuracy using cross validation. So a good way to evaluate a model is to use cross validation, just as we did in the previous videos where we did end-to-end project. And let's use the cross val score, right? So this one to train the data set. So our model is SGD classifier. So this is the all the features. This is the label only for 5 digit, means it will only check for the digit 5. CV is cross fault is 3, and score what we are getting is the accuracy. So this is the for 3 iteration it gives the 95 and 96 actually the accuracy in the remaining two cases. And that's amazing, right? If you're getting 95 accuracy, but do you agree on using only the accuracy, because accuracy can be a misleading in many cases? So let's uh, try to correct our hypothesis with the dummy classifier, right? So in this dummy classifier, what we are going to do, we are going to use the dummy classifier class and fit the models. And here we at the final, after doing the same step for with the dummy classifier, we are getting the 90. So our accuracy has been reduced to 95% reduction is there. So now we can see the uh, even using the some dummy classifier, we are getting the higher accuracy, which is incorrect, and there's a reason for that. And to answer that question, we have to look at the confusion matrix. So the general idea of a confusion matrix is to count the number of time instead of a class A as classified as a class B in the pair of A and B pair, right? For example, to know the number of the time classifier confuse the image of 8 with 0, and it would be like because many digits have the very similar representation, right? And to compute the confusion matrix, first need to have a set of prediction so that you can compare it with the actual target. So we have to do that prediction. So what we are going to use cross val predict in this case, not the cross val score like before. So in the prediction, it instead of giving the scores, it will give you the prediction for each iteration. And after calculating the prediction, we can build a confusion matrix that you can import from scikit-learn matrix with the this label and the prediction value. And you can see, so this is what our confusion matrix is. It's two areas, right? Two rows, two columns, and this represents. So this is the actual value. This is the rows are the actual value, the columns are the predictive value, and this is the uh, values of. If I yeah, this one is the value is a true negative, means where it correctly identify the non fives. This is a true positive. So this line is for true, this diagonal is for true, this diagonal is for false, false negative, false positive. And what's the perfection looks like? So what we are going to do, instead of we'll use the same labels as the perfect prediction, and then we'll create the confusion matrix. So this is what the perfect confusion matrix looks like. So this is all, you have the true negative and this is all the true positive. So there are no false prediction being done. And this is the what we call the perfection confusion matrix. To have more understanding of the confusion matrix, there are two more terms I want to highlight. One is the precision, which is nothing but a positive prediction. And the formula for that is true positive divided by true positive and false positive. And the second one is the recall, which is also called the sensitivity or true positive rate. So this is the ratio of the positive instance that are correctly detected by the classifier. And the formula for this is true positive divided by true positive and false negative. And this is what we have the confusion matrix representation. So what is mean by here is, so this is the true negative area and this is the true positive. As you can see, the digits 8, 3, 9, 2, 5 were perfectly identify the known five values, and this one is it is it is five digit. The digit which is represented by was perfectly identified. But in these two cases, though the value was five, but it was predicted as something else, and in this case, the six was predicted as five. So this is false positive, and this is false negative. So this is what the confusion matrix looks like. So what we did, just to do a quick recap, we imported our library, we fetched the dataset MNIST 784, and it has 70,000 rows and 784 columns, which is nothing but one digit represent 28 by 28. So that's these 784 features. And we have a one function plot digit. It just check for the first value, which is 5. The data set has already been divided into test and train and already suffered, and we trained the 5 detector. We are only checking for the digit 5, and after using the SDT classifier we were able to successfully predict. And then we'll start our conversation regarding the performance measure, because in the classification you have to use some performance measures, and those are the accuracy, precision, recall, and confusion matrix is the good way to have that information where the recall positive you have true positive to divided by true positive or false negative, and the precision is true positive divided by false positive. So that's what is it. It's there in the first part. I will continue our discussion. We'll talk more about the precision, recall trade-offs, and the other measures. Thank you.